Father from 19. Today is week 4 of deep learning and neural network course, and it is actually wait, day 8 in my challenge day. So let's start.
Welcome to the fourth week of this class. By now, you've seen forward propagation and back propagation in the context of a neural network with a single hidden layer, as well as logistic regression, and you've learned about vectorization and when it's important to initialize the weights randomly. If you've done the past couple of weeks' homeworks, you've also implemented and seen some of these ideas work for yourself. So by now, you've actually seen most of the ideas you need to implement a deep neural network. What we're going to do in this week is take those ideas and put them together so that you'll be able to implement your own deep neural network. Because this week's programming exercise is longer and just has a bit more work, I'm going to keep the videos for this week shorter so you can get through the videos a little bit more quickly and then have more time to do a significant programming exercise at the end, which I hope will leave you having built a deep neural network that you feel proud of. So what is a deep neural network? You've seen this picture for logistic regression, and you've also seen neural networks with a single hidden layer. So here's an example of a neural network with 2 hidden layers and a neural network with 5 hidden layers. We say that logistic regression is a very shallow model, whereas this model here is a much deeper model. And shallow versus depth is a matter of degree. So neural network with a single hidden layer, this would be a 2-layer neural network. Remember, when we count layers in a neural network, we don't count the input layer, we just count the hidden layers as well as the output layer. So this would be a 2-layer neural network, is still quite shallow, but not as shallow as logistic regression. Technically, logistic regression is a 1-layer neural network. But over the last several years, the AI and the machine learning community has realized that there are functions that very deep neural networks can learn that shallower models are often unable to. Although for any given problem, it might be hard to predict in advance exactly how deep a neural network you would want. So it would be reasonable to try logistic regression, try 1 and then 2 hidden layers, and view the number of hidden layers as another hyperparameter that you could try a variety of values of and evaluate on holdout cross-validation data or on your development set. Say more about that later as well. Let's now go through the notation we'll use to describe deep neural networks. Here is a 1, 2, 3, 4-layer neural network with 3 hidden layers, and the number of units in these hidden layers are, I guess, 5, 5, 3, and then there's 1 output unit. So the notation we're going to use is going to use capital L to denote the number of layers in the network. So in this case, L is equal to 4. And so that's the number of layers. And we're going to use n superscript L to denote the number of nodes or the number of units in layer lowercase l. So if we index this, the input, as layer 0, this is layer 1, this is layer 2, this is layer 3, and this is layer 4, then we have that, for example, n1, that would be this, the first hidden layer, would be equal to 5 because we have 5 hidden units there. For this one, we have that n2, the number of units in the second hidden layer, is also equal to 5. N3 is equal to 3, and N4, which is N capital L, is the number of units, is the number of output units is equal to 1, because here capital L is equal to 4. And we're also going to have here that for the input layer, N0 is just equal to Nx is equal to 3. Okay, so that's the notation we'll use to describe the number of nodes we have in different layers. For each layer L, we're also going to use AL to denote the activations in layer L. So we'll see later that for propagation, you end up computing AL as the activation G applied to ZL, and perhaps the activation is indexed by the layer L as well. And then we'll use WL to denote the weights for computing the values ZL in layer L. And similarly, BL is used to compute ZL. Finally, just to wrap up on the notation, the input features are called X, but X is also the activations of layer 0. So A0 is equal to X, and the activation of the final layer A capital L is equal to y hat. So A superscript square bracket capital L is equal to the predicted output, the prediction y hat of the neural network. So you now know what a deep neural network looks like, as was the notation we'll use to describe and to compute with deep networks. I know we've introduced a lot of notation in this video, but if you ever forget what some symbol means, we've also posted on the course website a notation sheet or notation guide that you can use to look up what these different symbols means. Next, I'd like to describe what forward propagation in this type of network looks like. Let's go on to the next video. In the last video, we described what is a deep L-layer neural network and also talked about the notation we use to describe such networks. In this video, you'll see how you can perform forward propagation in a deep network. As usual, let's first go over what forward propagation will look like for a single training example X, and then later on we'll talk about the vectorized version where you want to carry out forward propagation on the entire training set at the same time. But given a single training example X, here's how you compute the activations of the first layer. So for this first layer, you would compute Z1 equals W1 times X plus B1. So W1 and B1 are the parameters that affect the activations in layer 1, right? Remember, this is layer 1 of the neural network. And then you compute the activations for that layer to be equal to G of Z1. And if the activation function G depends on what layer you're at, then maybe we'll index that as the activation function for layer 1. So if you do that, you've now computed the activations for layer 1. How about layer 2? Say that layer. Well, you would then compute Z2 equals W2 A1 plus B2, and then so the activation of layer 2 is the weight matrix times the output of layer 1, so it's that value, plus the bias vector for layer 2, and then A2 equals the activation function applied to Z2. Okay, so that's it for layer 2, and so on and so forth, until you get to the output layer, that's layer 4, where you would have that Z4 is equal to the parameters for that layer times the activations from the previous layer plus that bias vector, and then similarly A4 equals G of Z4. And so that's how you compute your estimated output y hat. So just one thing to notice, X here is also equal to A0 because the input feature vector X is also the activations of layer 0. So we scratch out X, and we're going to cross out X and put A0 here, then all of these equations basically look the same, right? The general rule is that ZL is equal to WL times A of L minus 1 plus BL, there's a 1 there, and then the activations for that layer is the activation function applied to the values Z. So that's the general forward propagation equation. So we've done all this for a single training example. How about for doing it in a vectorized way for the whole training set at the same time. The equations look quite similar as before. For the first layer, you would have capital Z1 equals W1 times capital X plus B1, and then A1 equals G of Z1, right? And bearing in mind that X is equal to A0, these are just, the training examples stacked in different columns. You could take this, let me scratch out X, you can put A0 there. And then for the next layer, it looks similar, Z2 equals W2 A1 plus B2, and A2 equals G of Z2, right? We're just taking these vectors Z or A and so on and stacking them up. This is Z vector for the first training example, Z vector for the second training example, and so on down to the nth training example, and stacking these in columns and calling this capital Z, right? And similarly for capital A, just as capital X, all the training examples are column vectors stacked left to right. And then at the end of this process, you end up with y hat, which is equal to G of Z4. Oh, this is also equal to A4. And that's the predictions on all of your training examples stacked horizontally. So just to summarize, our notation, I'm going to modify this up here. Our notation allows us to replace lowercase z and a with the uppercase counterparts, because that already looks like a capital Z. And that gives you the vectorized version of forward propagation that you carry out on the entire training set at a time, where A0 is X. Now, if you look at this implementation of vectorization, it looks like that there is going to be a for loop here, right? So it's for L equals 1 to 4, or for L equals 1 through capital L, that you have to compute the activations for layer 1, then for layer 2, then for layer 3, and then for layer 4. So it seems that there is a for loop here. And I know that when implementing neural networks, we usually want to get rid of explicit for loops, but this is one place where I don't think there's any way to implement this without an explicit for loop. So when implementing forward propagation, it is perfectly okay to have a for loop that computes the activations for layer 1, then layer 2, then layer 3, then layer 4. No one knows, and I don't think there exists any way to do this without a for loop that goes from 1 to capital L, from 1 through the total number of layers in the neural network. So in this place, it's perfectly okay to have an explicit for loop. So that's it for the notation for deep neural networks, as well as how to do forward propagation in these networks. If the pieces we've seen so far looks a little bit familiar to you, that's because what we've seen is taking a piece very similar to what you've seen in the neural network with a single hidden layer and just repeating that more times. Now, it turns out that when you implement a deep neural network, one of the ways to increase your odds of having a bug-free implementation is to think very systematically and carefully about the matrix dimensions you're working with. So when I'm trying to debug my own code, I'll often pull a piece of paper and just think carefully through some of the dimensions of the matrix I'm working with. Let's see how you could do that in the next video. When implementing a deep neural network, one of the debugging tools I often use to check the correctness of my code is to pull a piece of paper and just work through the dimensions of the matrix I'm working with. So let me show you how to do that. Since I hope this will make it easier for you to implement your deep nets as well. So capital L is equal to 5, right? Count down quickly. Not counting the input layer, there are 5 layers here. So 4 hidden layers and 1 output layer. And so if you implement forward propagation, the first step will be Z1 equals W1 times the input features X plus B1. So let's ignore the bias terms B for now and focus on the parameters W. Now this first hidden layer has 3 hidden units. So this is layer 0, layer 1, layer 2, layer 3, layer 4, and layer 5. So using the notation we had from the previous video, we have that n1, which is the number of hidden units in layer 1, is equal to 3. And here we would have that n2 is equal to 5, n3 is equal to 4, n4 is equal to 2, and n5 is equal to 1. And so far, we've only seen neural networks with a single output unit, but later, in later courses, we'll talk about neural networks with multiple output units as well. And finally, for the input layer, we also have n0 equals nx is equal to 2. So now let's think about the dimensions of z, w, and x. Z is the vector of activations for this first hidden layer. So z is going to be 3 by 1. It's going to be a three-dimensional vector. So I'm going to write it as a n1 by 1 dimensional vector, or n1 by 1 dimensional matrix. Right? 3 by 1 in this case. Now, how about the input features x? X, we have two input features. So x is, in this example, 2 by 1. But more generally, it will be n0 by 1. So what we need is for the matrix W1 to be something that when we multiply an n0 by 1 vector to it, we get an n1 by 1 vector, right? So you have sort of a three-dimensional vector equals something times a two-dimensional vector. And so by the rules of matrix multiplication, this has got to be a 3 by 2 matrix. Right? Because the 3 by 2 matrix times a 2 by 1 matrix, or times a 2 by 1 vector, that gives you a 3 by 1 vector. And more generally, this is going to be an n1 by n0 dimensional matrix. So what we figured out here is that the dimensions of W1 has to be n1 by n0. And more generally, the dimensions of WL must be NL by NL minus 1. So for example, the dimensions of W2, for this, it will have to be 5 by 3, or it will be N2 by N1, because we're going to compute Z2 as W2 times A1. And again, let's ignore the bias for now. But so this is going to be 3 by 1, and we need this to be 5 by 1, and so this had better be 5 by 3. And similarly, W3 is really the dimension of the next layer, comma, the dimension of the previous layer. So this is going to be 4 by 5. W4 is going to be 2 by 4, and W5 is going to be 1 by 2. Okay? So the general formula to check is that when you're implementing the matrix for a layer L, that the dimension of that matrix be NL by NL minus 1. Now, let's think about the dimension of this vector B. This is going to be a 3 by 1 vector, so you have to add that to another 3 by 1 vector in order to get a 3 by 1 vector as the output. Or in this example, you need to add this, which is going to be 5 by 1, so it's going to be another 5 by 1 vector in order for the sum of these two things that I have in the boxes to be itself a 5 by 1 vector. So the more general rule is that in the example on the left, B1 is N1 by 1, right? That's 3 by 1. And in the second example, it is this is N2 by 1. And so the more general case is that BL should be NL by 1 dimensional. So hopefully these two equations help you to double check that the dimensions of your matrices W as well as of your vectors B are the correct dimensions. And of course, if you're implementing backpropagation, then the dimensions of dW should be the same as the dimension of W. So dW should be the same dimension as W, and dB should be the same dimension as B. Now, the other key set of quantities whose dimensions to check are these Z, X, as well as A of L, which we didn't talk too much about here, but because Z of L is equal to G of A of L applied element-wise, then Z and A should have the same dimension in these types of networks. Now, let's see what happens when you have a vectorized implementation that looks at multiple examples at a time. Even for a vectorized implementation, of course, the dimensions of W, B, dW, and dB will stay the same, but the dimensions of Z, A, as well as X will change a bit in your vectorized implementation. So previously, we had Z1 equals W1 times X plus B1, where this was N1 by 1, this was N1 by N0, X was N0 by 1, and B was N1 by 1. Now, in a vectorized implementation, you would have Z1 equals W1 times X plus B1, where now Z1 is obtained by taking the Z1s for the individual example, so that's Z11, Z12, up to Z1M, and stacking them as follows, and this gives you Z1. So the dimension of Z1 is that instead of being N1 by 1, it ends up being N1 by M, if M is the size of your training set. The dimensions of W1 stays the same, so it's still N1 by N0, and X, instead of being N0 by 1, is now all your training examples stacked horizontally, so it's now N0 by M. And so you notice that when you take a N1 by N0 matrix and multiply that by an N0 by M matrix, that together they actually give you an N1 by M dimensional matrix as expected. Now the final detail is that B1 is still N1 by 1, but when you take this and add it to B, then through Python broadcasting, this will get duplicated into an N1 by M matrix and then added element-wise. So on the previous slide, we talked about the dimensions of W, B, dW, and dB. Here, what we see is that whereas ZL as well as AL are of dimension NL by 1, we have now instead that capital ZL as well as capital AL are NL by M. And a special case of this is when L is equal to 0, in which case A0, which is equal to just your training set input features X, is going to be equal to N0 by M as expected. And of course, when you're implementing this in backpropagation, we'll see later you end up computing dz as well as dA, and so these will of course have the same dimension as z and a. So I hope the little exercise went through helps clarify the dimensions of the various matrices you'll be working with. When you implement backpropagation for a deep neural network, so long as you work through your code and make sure that all the matrices dimensions are consistent, that will usually help go some ways toward eliminating some class of possible bugs. So I hope that exercise for figuring out the dimensions of the various matrices you'll be working with is helpful. When you implement a deep neural network, if you keep straight the dimensions of these various matrices and vectors you're working with, hopefully that'll help you eliminate some class of possible bugs. It certainly helps me get my code right. So next, we've now seen some of the mechanics of how to do certain forward propagation in a neural network. But why are deep neural networks so effective, and why do they do better than shallow representations? Let's spend a few minutes in the next video to discuss. We've all been hearing that deep neural networks work really well for a lot of problems. And it's not just that they need to be big neural networks, is that specifically they need to be deep or to have a lot of hidden layers. So why is that? Let's go for a couple examples and try to gain some intuition for why deep networks might work well. So first, what is a deep network computing? If you're building a system for face recognition or face detection, here's what a deep neural network could be doing. Perhaps you input a picture of a face, then the first layer of the neural network you can think of as maybe being a feature detector or an edge detector. In this example, I'm plotting what a neural network with maybe, in this a feature detector or an edge detector. In this example, I'm plotting what a neural network with maybe 20 hidden units might be trying to compute on this image, with the 20 hidden units visualized by these little square boxes. So for example, this little visualization represents a hidden unit that's trying to figure out if, where the edges of that orientation in the image. And maybe this hidden unit might be trying to figure out where are the horizontal edges in this image. And when we talk about convolutional networks in a later course, this particular visualization will make a bit more sense. But informally, you can think of the first layer of the neural network as looking at a picture and trying to figure out, where are the edges in this picture. Now that it's figured out where are the edges in this picture by grouping together pixels to form edges, it can then take the detected edges and group edges together to form parts of faces. So for example, the edges in this picture by grouping together pixels to form edges, it can then take the detected edges and group edges together to form parts of faces. So for example, you might have a little neuron trying to see if it's finding an eye, or a different neuron trying to find that part of the nose. And so by putting together lots of edges, it can start to detect different parts of faces. And then finally, by putting together different parts of faces, like an eye or a nose or an ear or a chin, it can then try to recognize or detect different types of faces. So intuitively, you can think of the earlier layers of a neural network as detecting simpler functions like edges, and then composing them together in the later layers of a neural network so that it can learn more and more complex functions. These visualizations will make more sense when we talk about convolutional nets. And one technical detail of this visualization, the edge detectors are looking in relatively small areas of an image, maybe very small regions like that. And then the facial detectors, can look at maybe much larger areas of the image. But the main intuition what you take away from this is just finding simpler things like edges and then building them up, composing them together to detect more complex things like an iron nose, and then composing those together to find even more complex things. And this type of simple to complex hierarchical representation or compositional representation applies in other types of data than images and face recognition as well. For example, if you're trying to build a speech recognition system, it's hard to visualize speech, but if you input an audio clip, then maybe the first level of a neural network might learn to detect, low-level audio waveform features, such as, is this tone going up, is it going down, is it white noise or sibilant sound like s, right? And what is the pitch? But it can detect low-level waveform features like that. And then by composing low-level waveforms, maybe you'll learn to detect basic units of sound. So in linguistics, they're called phonemes. But for example, in the word cat, the k is a phoneme, the a is a phoneme, the t is another phoneme, but it learns to find maybe the basic units of sound. And then composing that together, maybe you learn to recognize words in the audio, and then maybe you can compose those together in order to recognize entire, phrases or sentences. So a deep neural network with multiple hidden layers might be able to have the earlier layers learn these lower level simpler features, and then have the later deeper layers then put together the simpler things that's detected in order to detect more complex things, like recognize specific words or even phrases or sentences that you're uttering in order to carry out speech recognition. And what we see is that whereas the earlier layers are computing what seems like relatively simple functions of the input, such as where are the edges, by the time you get deep in the network, you can actually do, surprisingly complex things, such as detect faces or detect words or phrases or sentences. Some people like to make an analogy between deep neural networks and the human brain, where we believe, or neuroscientists believe, that the human brain also starts off detecting simple things like edges in what your eyes see, and then builds those up to detect more complex things like the faces that you see. I think analogies between deep learning and the human brain are sometimes a little bit dangerous, but there is a lot of truth to um, this being how we think the human brain works, and that the human brain probably detects simple things like edges first and then puts them together to form more and more complex objects. And so that has served as a loose form of inspiration for some deep learning as well. We'll say a bit more about the human brain, or about the biological brain, in a later video this week. The other piece of intuition about why deep networks seem to work well is the following. So this result comes from circuit theory, which pertains to thinking about what types of functions you can compute with different AND gates and OR gates and NOT gates, basically logic gates. So informally, they're functions you compute with a relatively small but deep neural network. And by small, I mean the number of hidden units is relatively small. But that if you try to compute the same function with a shallow network, so if you aren't allowed enough hidden layers, then you might require exponentially more hidden units to compute. So let me just give you one example and illustrate this a bit informally. But let's say you're trying to compute the exclusive or the parity of all your input features. So you're trying to compute x1, x4, x2, x4, x3, x4 up to xn if you have n or nx features. So if you build an XOR tree like this, right? So first compute the XOR of x1 and x2, then take x3 and x4 and compute their XOR. And technically, if you're just using AND, OR, and NOT gate, you might need a couple layers to compute the XOR function rather than just one layer. But with a relatively small circuit, you can compute the XOR, right, and so on. And then you can, build really an XOR tree like so, until eventually you have a circuit here that outputs, well, let's call this y, that outputs y hat equals y, the exclusive or the parity of all of these input bits. So to compute the XOR, the depth of the network will be on the order of log n, right, with this type of XOR tree. So the number of nodes, or the number of circuit components, or the number of gates in this network is not that large. You don't need that many gates in order to compute the exclusive OR. But now, if you're not allowed to use a neural network with multiple hidden layers, with, in this case, order log n hidden layers, if you're forced to compute this function with just one hidden layer, right, so you have all these things going into, set of hidden units, and then these things then um, outputs y. Then in order to compute the parity of x, or to compute this XOR function, this hidden layer will need to be exponentially large, because essentially you need to exhaustively enumerate all 2 to the n possible configurations, or on the order of 2 to the n, possible configurations of the input bits that result in the exclusive OR being either 1 or 0. So you end up needing a hidden layer that is exponentially large in the number of bits. I think technically you could do this with 2 to the n minus 1 hidden units, right? But that's the order 2 to the n. So it's going to be exponentially large in the number of bits. So I hope this gives us 2 to the n. Of course, to compute large, you don't need that. The number of nodes or the number of the XOR, the depth of the network will be on the order of log n, right? Of this type of XOR tree. So the number of nodes or the number of circuit components or the number of gates in this network is not that large. You don't need that many gates in order to compute the exclusive OR. But now, if you're not allowed to use a neural network with multiple hidden layers, with, in this case, order log a neural network with multiple hidden. But now, if you're not allowed to use a neural network with multiple to compute things, then exponentially of the input bits that result in the exclusive OR being either 1 or 0. So you end up needing a hidden layer that is exponentially large in the number of bits. I think technically you could do this with 2 to the n minus 1 hidden units, right? But that's the order 2 to the n. So it's going to be exponentially large in the number of bits. So I hope this gives a sense that there are mathematical functions that are much easier to compute with deep networks than with shallow networks. I have to admit, I personally found the result from circuit theory less useful for gaining intuitions, but this is one of the results that people often cite when explaining the value of having very deep representations. Now, in addition to these reasons for preferring deep neural networks, to be perfectly honest, I think the other reason the term deep learning has taken off is just branding, right? These things used to be called neural networks with a lot of hidden layers, but the phrase deep learning, is just a great brand. It just is so deep, right? So I think that once that term called on, that really neural networks rebranded, or neural networks with many hidden layers rebranded, helped to capture the popular imagination as well. But regardless of the PR branding, deep networks do work well. Sometimes people go overboard and insist on using tons of hidden layers, but when I'm starting out with a new problem, I'll often really start out with even logistic regression, then try something with 1 or 2 hidden layers and use that as a hyperparameter, use that as a parameter or hyperparameter that you tune in order to try to find the right depth for your neural network. But over the last several years, there has been a trend toward people finding that for some applications, very, very deep neural networks, with maybe many dozens of layers sometimes, can sometimes be the best model for a problem. So that's it for the intuitions for why deep learning seems to work well. Let's now take a look at the mechanics of how to implement not just forward propagation, but also back propagation.
Before I start recording, I'm going to recap what I learned today. Uh, So today I learned that compared to logistic regressions, which is a shallow neural network in the technic in terms of technical means, and one hidden layer neural network, and compared with that, with those networks, how the deep neural network formed and what is the shape of the deep neural network. So in this case, if we take this example in the five hidden layers, we can say that this is a kind of deep neural network. Um, Deep neural network that is a network that having many hidden layers. So technically, a shallow network like logistic regressions is also neural network, but there are also some kind of functions that deep neural network only can obtain. And these reasons will be explained in the last section. So after that, uh, I overviewed the fourth propagation in deep neural network. And for the generalized form in the equations, we use for each training examples, not the entire one. We do use small l here. And when we compute g, which is on the layer L, we need to use the previous activations from the previous layer. But the weights and the bias is for about the current layer. So, and the activation for current layer will be represented as GL and use parameter as a GZL of the current layer. And this is for just one training example. And if we vectorize this for M training example, we can vectorize with the capital case by using these equations. But it's mm, not that has big difference between previous one, like the shallow networks. We already seen these equations in these networks. And also, when I do some programming assignment from this course, I always suffer from dimensional metrics. And the professor mentioned that to getting the metric dimension right is very important. And I wrote this in this section. Let's say that we have these five hidden layer neural network. And by using a superscript for each layer, we can uh, represent the number of units for each layers and hidden layers. And if we write down the first equation for just one training example, we can say we can write the superscript 1 is equal to W1 W superscript dot product X plus B superscript 1, which is bias. And the number of hidden units are here, 3. So it's triggered that we know these two dimensions, so we can determine that what the dimensions of the W1 matrix is. So the row dimension, the number of rows will be it depends on the dimension of Z, and the column dimension is depends on the X input X. So we can write here is with the more generalized form, we can use the layer index in the superscripts like this. And also DWL and DBL have same direction when we compute vector propagation later on. And if we vectorize this equation in the M training example, the dimension of WL and BL will be constant, and also for B bias, It's constant because we're gonna use Python broadcasting. And but for Z and X will be different with the one training example because we use n training example here. Next, how why the representation works well. Next one, the professor handled the topic of why deep representations work well. For example, we have image detection problem here. We the input as the input we have an image for a human face, and the first hidden layer we can detect some kind of edges inside of this image, like this hair and part of ear. And by composing these all together, we can set up part of faces like nose, eyes here, as you can see. And then composing these part of faces into a face, we can get a various type of face, like for a human. The whole process will be like this. So the intuition for this example is simply find simpler things first and compose it together to form more complex one like face. The simpler one is kind of edges or points and other similar things. And another statements about why deep NN works well. It's about this statement, but it's more easier to understand this statement with this specific example for intuition. Let's say that we want to compute uh, exclusive OR operation for each features from x1 to xn. So for example, if we are allowed to use many hidden layers, you can think that we can use a hidden layer for x1, x2 for the one, and x2, x3, x4 for the next one, and so forth. So we can represent the tree structure as in the depths of all log n levels. But on the other hand, if we are not allowed to use many hidden layers, the complexity goes up to all exponentially. Like this, we have n features, and we need to compute all these XO operations for each hidden layer. So there will be exponential time complexity. So that's all for today's recording, and thanks for your watch.